Okay, welcome everybody to the fourth and final part of the fifth annual Montreal Oscillometry Summer Seminar. The program is, as you've received now over the past month, and the stats pretty much remain the same, except I was able to go through the Zoom platform and understand their stats a little bit better. So the reality is that we've been averaging 90 participants per session from 25 countries for the 21 presentations we've been having. We'll see what happens today. Here's a graphic that just shows the distribution. So obviously there's a North American predominance here, but we have a nice spectrum of countries from all continents. And I'd like to do a special shout out to our industry partners who have been making this and other events happen. To remind everybody, if you've missed a session, you can catch it on the REG website. Due to holidays, last week's is not yet up, but it will be up there next week along with this week's seminar for future reference. And finally, I'm happy to announce, and optimistic, hopefully not overly optimistic, that we have dates for next year's seminar live in Montreal, sanitary conditions permitting. So it'll be the last Thursday and Friday of July with our now famous oscillometry supper, where, as I like to brag, the business gets done. This is where the networking is. Projects have been hatched around this dinner table, and happily publications have resulted. So anybody who can make it, you'll be more than welcome. You now have the dates for your agenda. And again, a big shout out to the industrial partners who make that dinner in particular possible, enjoyable, and memorable. So with that, I'm going to stop sharing my screen and turn the floor over to Jason Bates, who's coming to us live from somewhere on the East Coast of the United States. And he's going to talk to us about breath-driven oscillometry. The patient does all the work. And we're really privileged to have as a discussant David Kaska from the University of Iowa. And he's going to lead off with some questions and monitor the discussion. And then they'll change hats in terms of the presenter discussing goals for the next talk. So Jason, over to you.
Thanks, Ron. Let me just get my screen sharing sorted out here. Can you see that?
Yes, I can. And before I mute, I'm just going to shout out to Jeff Fredberg in Boston. We got a great chest shot of you, Jeff, but you need to put your microphone up to face level. Thanks.
Okay, well, thanks very much, Ron. Great work again organizing this terrific seminar. First of all, let me apologize for not having attended the previous sessions. My wife and I just went through a big move, and things were a bit chaotic, but they're settling down now. So I'm very glad to be able to join the final session. I also want to thank Ron for coming up with the title for my talk. And I love the sort of implications of patient abuse. So let me begin. Disclosures, some minor consultancies there. Now let me jump right in. So a first introductory slide, and this is really superfluous, I think, but I'm going to say it anyway. So the synopsis of measuring respiratory impedance by oscillometry is that you have some kind of an oscillating device, typically a loudspeaker driving flow in and out of the subject's mouth, and you measure pressure at the airway opening, PAO, and the delta pressure, in this case, across a pneumotachograph to measure flow. And you measure those two. Can you hear me okay, everyone?
Yeah, I'm just going to do some muting and Charlie will join me and we'll get it. So carry on.
Yeah, so you measure oscillatory pressure and flow. And then you do some computer processing of those signals and you end up with impedance, and it has a real part and an imaginary part. So that's about the simplest statement of what actually happens, I guess, leaving out all the details, but everybody's familiar with all that. So in a sense, you could say, what is the central requirement for this to work? And that is that the pressure across the pneumotract and the airway opening pressure must oscillate at some frequency, preferably in multiple frequencies. Now, oscillations are typically produced by an active device that pumps air back and forth. And the major examples are a loudspeaker or a piston, and I'm sure you've seen multiple examples of those in the previous sessions of this conference. But it turns out that this does not have to be the case. You just have to have some way in which pressure and flow at the mouth oscillate. Now, the first time I saw a formal approach to doing this in a different way was the work by Arthur Johnson from University of Maryland. And I first met him probably 35 years ago when he was working on this. And he came up with a thing he called the airflow perturbation device, which, and this is taken from his paper, looks like this. And you have a, he's got a diagram of a pneumotachograph here with the mouthpiece going to the subject. And the subject is just breathing normally. And in front of the pneumotach, connected to it, you have a rotating wheel with an alternating screen and then open part. So what that does is it alternately changes the airflow resistance, and that causes oscillations at the mouth. But the patient is producing all the power necessary to cause those oscillations. There's no motor generating the oscillations in the device itself. And he was able to show that you can measure particularly resistance in what looks like a reasonable way. And I also remember way years back when I was a fellow in the Meakins, that it was a sort of, generally accepted that people had this idea a long time ago that if you blew into some flexible tube that rattled at the end and made a rude noise, that you might also generate oscillations, and people wondered whether you could measure impedance that way. So it's an idea that's been around for a while. So what we decided to do recently at the University of Vermont is to formally test this in clinically approved devices that generate oscillatory airflow for the purposes of clearing mucus, particularly in cystic fibrosis patients. And we use two devices. One is the Acapella shown at the top, and then is the VPEP at the bottom. And they use slightly different mechanisms for generating airflow oscillations when you breathe in and out of them. But this is a kind of a basic design. You have some kind of a steel ball that occludes a valve, kind of like a heart valve in a way. And then when you blow through it, the ball goes up and then falls down and up and falls down, and it rattles backwards and forwards. And when you blow on these things, you really can feel the oscillations. And that's the whole point of them clinically, actually, is that they'll generate oscillations that go down into the chest and hopefully help you clear mucus. So we published a paper recently on this in the Journal of Applied Physiology, and that's what I'm just going to talk about briefly. This study was done primarily by Greg Roy, who was a senior medical student at the time, along with my other colleagues you see there. So what we did was we tested the Acapella and the VPAP as people breathe through them, and we used a FlexiVent with a large piston designed for humans with no inspiratory-expiratory valves to generate broadband flow in order to measure respiratory impedance as a standard. And you can see here is the volume flow, the volume acceleration, and the pressure on the left from the FlexiVent. And you can see just by looking at it, that's got multiple frequencies. The Acapella in the middle and the VPEP on the right also oscillate, but only during expiration, and that's the way they're designed. And you can see that it looks like more of a pure single frequency oscillation there. I mean, you can just see that by looking at it. But anyway, they're generating oscillations both in flow and pressure at the mouth. So we have flow and pressure oscillations in the mouth. Can we use those in the standard way just to measure impedance? Here is an example of a couple of breaths of flow from the Acapella and the VPEP, and they look fairly similar. When you do a power spectral analysis on those signals, on the expiratory portions, you see that they're pretty narrow band. I mean, over here, I hope you can see my cursor, the power is centered around about 15 hertz. It's a little bit above the normal resonant frequency, but not far from it, and it's pretty narrow band. So basically, these things are oscillating like single sine wave oscillators. Because they're above the resonant frequency, we need to consider impedance. We need to consider inertance when we're analyzing them. And so we fit this equation of motion to the measurements of pressure and flow and volume acceleration, where we would extract values for a respiratory elastance, resistance, and inertance. And the reason that we did this way rather than doing the usual Fourier domain analysis is because it wasn't a clear a priori what the frequency of oscillation was going to be from those devices and whether it was going to stay the same throughout the breath or throughout the expiration. So I just decided to go straight to the time domain model, estimating the parameters that was pretty clear you had to include. So here we show for 8 subjects, the comparison of the R, E, and I values from the flex event, which is the standard, if you like, and the a cappella and the VPAP. And what you can see is, at a quick look, is that the resistance values agree quite well. The elastance values and the inertance values don't agree nearly so well, and some of them are even negative. There's the 0 line from the a cappella and actually from the VPAP. Sorry, that should be one of these things. Should be a closed. That should be a closed triangle. Sorry. The flex event values are all pretty normal, as you'd expect. When we do a Bland-Altman plot of those signals, you find that the variation, the difference between the VPAP and the flex event, or the a cappella versus the flex event, is, you know, plus or minus 1 to 1.5 centimeters of water times seconds per liter. So not a huge amount, but the difference is where the elastance and resistance are very large. So that's to be expected. I mean, we interpreted that in a fairly obvious way, in that the resistance of that model is determined entirely by the real part of impedance. And we have essentially one value at one frequency, and we can estimate one parameter, which is resistance. The problem with the reactive part is that you have both elastance and inertance to evaluate. And the signals that are produced, the oscillations that are produced by the a cappella and the VPAP, just aren't broadband enough to get a good fix on those two simultaneously. But we also had our subjects do maximal controlled expirations from TLC down to RV in triplicate. And you can see that if we look at the flex event here, for example, and this is for every subject we studied, here's the representative subject, you know. The flex event are the top ones. They're all pretty representative now that I look at it. The signals are reproducible, and we find that resistance, which is probably something close to airway resistance, is decreasing progressively throughout the breath. The a cappella and the VPAP actually do similar things. They decrease throughout the breath, and they're pretty reproducible. Some weird things happen at the beginning and the end of the breath, and that's because it takes a little while to get those oscillations going, and then when the expiration ends, they stop. But from the point of view of estimating resistance, this looks pretty promising. Now, I just wanted to add another thing here while we're on the topic of not using active oscillation generators to measure impedance. About 25 years ago, when I was at McGill, I had a student, Ev Bijawi, who did a nice study as part of a PhD, calculating what we ended up calling output impedance of the lung. We first of all called it input impedance, and one of the reviewers said, well, you can't do that. It's not input impedance. So we said, okay, we'll call it output impedance, and they went with that. But basically what Ev did, and I should say, by the way, Ev was a wonderful person, and she died tragically of a brain tumor a number of years ago, which is incredibly sad for me. But she was a wonderful person and did a great study. And so what she did was have someone just breathe on a pneumotach where we could measure pressure and flow. We had a valve in front of this, and so she would have people just remain apneic with an open glottis at FRC, which took a little practice. And she would measure the tiny cardiogenic oscillations produced in flow when the glottis was open, when the valve was open. And then she'd close the valve and measure the tiny oscillations in pressure that were generated by the cardiogenic oscillations. And she used heart sounds to phase match those signals. So this is flow and pressure, and this is where the valve closes. Flow is present when the valve is open. Pressure is present when the valve is closed. Here are the heart sounds. She lined those signals up and calculated ensemble averages and was able to calculate impedance, and again, compared it to a standard measurement of impedance. I think we used the flex event again, I can't remember. And in 5 subjects. And there is some difference between these signals. It's a bit hard to see, but the gold standard measurements are in the diamonds, and the output impedance measurements are in the circles. So there's a little bit of a difference. But what you notice if you look carefully, and I won't go into it, is that the reactive part seems to lie pretty well flat along zero, whereas the resistive part, measured by the cardiogenic oscillations, does show this negative frequency dependence and is, not exactly the same as the standard measurement, but heading in the right direction. And there's a variety of that. It could have been different amplitudes and so forth. And she got one subject and had them do exercise at various levels and compared it at rest and looked at the resistive part of frequency from 2 to 8 hertz, and they lined up pretty well. So of course, the frequencies you're able to measure depended on the spectral content of the cardiogenic oscillations, but it's gave what looks like a reasonable estimate of resistance of something. And we wondered what that was. And we figured, well, if the heart's banging into the lungs and squirting air out, it might be the resistance of the upper airways that we're measuring, which could explain why it's a little bit lower than the complete airway tree resistance measured by a standard impedance device. So in conclusion, measurement of respiratory impedance obviously requires oscillations in mouth pressure and flow, and we tend to think that that requires some kind of standard oscillator. But the problem with standard oscillators, if you want to think of it as a problem, is that they require a motor and a power source, and both of those things tend to have iron cores in them, which makes them heavy. Now, modern technology can make even a heavy thing very light, but still, it's extra equipment, which does tend to have some mass. And we were wondering whether it might be possible to make a device which did away with all of those things and just could have a much lighter, more ambulatory device. We're still working on that as a potential practical concept. But we studied the VPEP and the a cappella just to gain proof of concept that this could actually be done. So they don't have to be oscillated by an externally powered device, as I said. The breath-driven oscillations provide ZRS, and I should have said they provide resistance measurements that are similar to that measured by a conventional device. The reason they don't do terribly well with the reactive part is because they're single frequency devices. If we could come up with a breath-powered oscillator that had multiple frequencies, I am certain that that problem would go away. And even oscillations generated by the heart provide a measure of respiratory impedance. So I'd like to acknowledge the authors on those various papers, my colleagues Anne and David, Ev and Pierre from the previous study, and Nirav, our engineer, and Olivia, the coordinator who did a lot of these patient-related stuff and some funding there. I even have to, it's been a while since I've acknowledged the Canadian MRC now in our now it's got a different name. What is it? Well, whatever it is. But anyway, back in my day, it was the Medical Research Council. So thank you. I'll take questions.
Okay, well, Jason, thanks for a very surprising talk. You're always a source of new information, at least for me. I'm going to hand the podium over to David Kaska to lead off discussion. So over to you, please, David.
Jason, great stuff. Really great as usual. And yeah, your device certainly reminded me of the airflow perturbation device of Art Johnson. I did see that work at the University of Maryland many years ago with George Barnes. With the a cappella, I'm really curious. What are the determinants of the frequency? Is it the density of the ball? Is it the geometry of the connectors? Is that anything that you can change depending on the design of the device?
Well, I mean, the answer is all of the above. And some a cappella devices actually have a very clever adjustable magnet where you can change the position between a stationary magnet and the metal thing that's oscillating to change the spring constant, basically, and hence the oscillatory frequency. So essentially the way these things work is they they have a resonant frequency in them, which involves some kind of mass, and you hit at that resonance. And it's close to the resonant frequency of the respiratory system itself normally, which is probably a design intentionally, I would imagine, because it might help move mucus a bit more effectively. I will tell you, we've spent a lot of time in the lab, particularly my engineer Nirav, who's a 3D printing pilot, enthusiast. We have tried all sorts of ways to come up with something that oscillates, that will produce multiple frequencies. We've exploited the Bernoulli effect and all sorts of things. And so far, we've kind of done it. We haven't come up with something that I would say is actually successful. So we're still working on that. But that's a pure engineering problem.
Multiple frequencies simultaneously, or
yes, yeah, multiple frequencies simultaneously.
So you can get something more broadband.
Right.
And it looked like this was oscillating only during exhalation. I assume you could just configure maybe 2 with different valves to do inspiratory as well. And the data that you showed going from TLC to, I assume, RV, were these were slow vital capacities?
Yes, they were slow and controlled.
So you know, probably the subjects were not flow limited when they were doing.
No, well, they were normal subjects. We haven't done a formal study with asthmatics or anything like that. So they certainly were not flow limited. The other thing you got to think about is, wonder about is, when somebody is breathing, they're activating their chest wall muscles, obviously. And that's going to presumably change the mechanical properties of whatever it is you're measuring somehow. So it's not an exact comparison between someone who's being, you know, passively oscillated necessarily and someone who's breathing enough to make one of these things vibrate. So there's a number of subtleties involved here.
Okay. And then I do remember the work that you did with Eve on output impedance, you know, generating flow perturbations from cardiogenic oscillations. And I was always curious, certainly with young, healthy subjects, you expect to see a sinus arrhythmia with the heart rate varying between inspiration and expiration. It could be pretty profound for somebody who's young and healthy. Is that an issue at all? It seems like you're trying to estimate impedance with a moving target, depending on what the heart rate might be.
Well, that's a good point. I mean, I showed you that example of that ensemble averaged, those ensemble average oscillations, and they weren't all exactly the same. So we're sweeping some of that under the carpet. The challenge there, of course, is you're not measuring the pressure and flow oscillations at the same time. You need to phase match them somehow. So if you could line up oscillations in flow before valve closure and oscillations in pressure after valve closure at the same point in the breath cycle, you might be able to correct for sinus arrhythmia. I don't know. We didn't go to those lengths.
I wonder how broadband things would be if you had somebody with atrial fibrillation or some real
great measurements. Yeah.
Yeah, that's great. Well, why don't I open it up for questions from the audience? And I don't know how we do this, Ron. People raise their hand or put it into the chat box.
But both ways, the polite people raise their hands. Folks like me and Charlie generally just shout out. So I'll let you go both ways. I can see Peter Calverley, for example, is up from Liverpool, and he's got his hand up. Why don't we start with him? And I think Ramon and Cindy are also raised hands. I'm on the gallery view, David, so that's how I know what's going on with them in case you still want to speak with you.
Yeah,
yes, and Ramon's got his hand up on my gallery as well. So I'll just, I mean, great stuff, as always, innovative, Jason, great stuff. I just wonder how sensitive this might be to breathing pattern. In other words, how much signal do you need to get a statement at a given frequency?
Yeah, well, if the breathing pattern changes the nature of the device that's oscillating, then there will be some sensitivity to that. But of course, as you breathe, you are changing lung volume and flow, and so you're getting some kind of an intra-breath measurement. So all of these things potentially have an effect. And if you're measuring things carefully, presumably you can decide where you are in the breath and what the flow is and so forth, and maybe get intra-breath measurements. Well, in fact, we kind of got intra-breath measurements. But in that last slide I showed. It turns out that these devices don't seem to change their frequency very much with the
Right.
breeding pattern. I think the reason is because they have a fixed resonant frequency based on their attributes, and you hit that and pretty much stay there. But like I say, if we can crack this multi-frequency simultaneous problem in a practically realizable way, we may have to take those kinds of things into account.
Yeah, sure. Great, thanks.
A question from Julian Allen in the in the box. May have misheard. Did you say resistance decreases during exhalation, but shouldn't it be increasing? Yeah, that's a good point. Are you?
Good point. Yeah, actually, I guess I should have thought about that a bit more carefully. It's a while since I've read my own paper. If it is truly airway tree resistance, then it should decrease. It should increase throughout exhalation. That's quite correct. However, this is a sort of a frequency at around about 14 hertz, and it involves the chest wall as well. And so there is some Newtonian tissue component in there as well. And my guess is that that's probably what is causing this effect, because when you go to high volumes, you're stretching those tissues, you're increasing the tension in the tissues, and almost inevitably their resistive properties are going to increase as well. So if I had to sort of think quickly on my feet and get around that, good question, that's what I would propose.
Thanks, Jason.
Great to see a force vital capacity where somebody's hit the flow limitation envelope on the flow volume curve.
Jason, sorry.
Go ahead. I'm sorry, Ron.
I just wanted to challenge Jason on his explanation. I thought that the tissue resistance was most predominant at this ultra low frequencies, like well below 5 hertz, 1, 2, 3 hertz.
Most of it is, but I did work again back in the Meekins years ago using the alveolar capsule technique in closed chest dogs that showed that there is a pure Newtonian component to the chest wall tissues, which I'm presuming behaves this way. And I will remember, I got to tell you this, around about that time, we had a visit from Jerry Mead. And I thought when I discovered this, oh, this is new information. This is kind of cool. And I remember talking about this to Jerry Mead. And before I even told him what the result was, he said, oh, yes, there's a Newtonian component in the chest wall. And I thought, wow, first of all, this guy knows a lot of stuff. And then I realized that, maybe it wasn't as new as I thought it was.
I see questions from Raymond and Cindy. Why don't we can do Raymond first.
Yeah, thanks, Jason, for this elegant study. I have a question, a technical question on data processing. You carry out fitting in the time domain with a resistance, elastance, inertance model. And by contrast, in FOT with the device, conventional device, you are computing resistance in a non-parametric way by just computing the resistive part of the Fourier transform. Yeah. My question is, if the model is really far away from the resistance, inertance, elastance, and you fit the data in the time domain with this model, with this parametric model, you are somehow loading the resistance parameter with the lack of fitness of the imaginary part. So my question is, why did you select to compute resistance by fitting in the time domain instead of just computing the Fourier transfer of the signals and compute resistance at the peak frequency? Did you try if there is a difference?
I didn't try. I didn't investigate that to see if there was a resistance. So from a purely technical, practical point of view, you may be right in the sense that fitting in the time domain versus calculating the Fourier domain can have a difference. If you're dealing with an RLC system that is linear, in principle, it won't make a difference. The reason I decided to do that was because a priori, I didn't know what frequency these oscillators were going to be oscillating at, and I didn't know if it was going to be stable. So I saw myself doing it in the frequency domain and then chasing frequencies around throughout the expiration, all that kind of stuff. And I thought, oh, to hell with it. I'm just going to fit the whole thing in the time domain with what I thought was a reasonable model. And I fit the same model to the FlexiVent data, which was broadband. I actually had 19 frequencies in it, and it fit very well as well, because we're dealing with healthy, normal subjects. So I didn't expect any particularly weird mechanical behavior. So I don't know. I'm not trying to say that it's not worth doing a comparison, because sure it is. Those things are always worth doing. But the reason I did it was because a priori I didn't know what frequencies to be going after.
Thank you.
All right, Cindy.
I guess I better be quick. Hi, Jason. It's good to see your face.
Yeah, likewise.
Thanks. I have two questions, and I might be thinking about it in completely the naive way, and in which case this will be an excellent educational moment for me. But my first question was, I think what it reminded me of was a dependent source, and it's been a while since first year uni, but it's kind of related to Peter Calverley's question, I guess, because what you have is, instead of an active voltage or current source, you've got a dependent source that is dependent on how much effort the patient puts in. Do you have some way of characterizing how dependent on effort it is? And my second question was, the other thing it reminded me of was the interrupter technique from ages ago, which I'm sure you also remember. I mean, you mentioned your problem with the devices only having, effectively single frequencies. The interrupter technique, and I know that would have involved a motor, but maybe it doesn't have to. That would have generated square waves that arguably would give you broader range of frequencies if you can get the patient to somehow generate square waves by interrupting flow in some way. Just a thought.
Yeah, well, good questions. What was the first one? Sorry, because I was thinking about the second one.
Oh, right. Yeah. The first one was that, essentially a similar question to Peter Calverley. They're dependent sources. How dependent are they on the patient effort?
Well, those a cappella and VPAP do take a little bit of an effort to get going. They're for people who are breathing fairly deeply. So presumably there's going to be some dependence of the measurements on the effort. How much that is, I couldn't tell you at this point because we haven't investigated it. But it's a good point to bring up.
It's just reminiscent of these dependent sources that we had to learn back in first year electrical engineering.
Oh, right. Yeah, sure. In terms of the interrupter technique, that is a good point. In fact, I did a lot of work. When I first got into lung mechanics as a fellow at the Meakins, I became effectively Mr. Resistus Interruptus, I used to like to say. That's what I focused on. So I learned a lot about lung physiology by looking at that. And you're right, if you get a square wave interruption, which has a sort of an infinitely broad spectral content in principle, you can do an instantaneous interruption. And you can calculate an impedance from a single interruption. The advantage practically from a signal processing point of view of continuous oscillations is you get a much better signal to noise effect. You get much more robust measurements. Yeah. If you could have some kind of a spring-loaded trapdoor or something which automatically slams shut at a certain point. Yeah. But in fact, essentially what the a cappella is kind of like that. It's kind of like a continuous repetitive interrupter technique at a particular frequency. So they all sort of come together under the same kind of theoretical umbrella when you think about these things. I
guess the question is what is tweakable to get you that square wave that you want, because currently obviously it's a single frequency device.
Right. Well, well, some of the subjects actually gave reasonable resistance and elastance measurements, which meant there must have been some breadth to their spectral content. And it could have been because it's not producing a pure sine wave, but it's kind of on, off, like that. Kind of like an impulse oscillometry kind of thing,
Thanks very much, Jason.
All right, Jason, thank you very much. I think we're a little bit over time, so.
So you're next, right, Dave?
Yes, I'm next, yeah. Share my
So
screen.
while David gets the screen up, Jason, one last quick question. Did you control for upper airway shunting with your device? I didn't remember from the picture if there was cheek support or not. How would that impact on the result?
We did do cheek support, yeah. So it was the same kind of thing as with when we used the flexi-dental oscillator, we had subject supporting the cheek. So yes, that's the same consideration. The only way you can get around that is having an oscillator at the chest wall, really.
Everybody can see my screen.
Very well.
Good. Okay. Thank you again for the invitation to speak. I'm sorry, I also missed the first couple of these being on service in the ICU. So, but I did get to attend last week. So I'm going to be looking at oscillometric perspectives of liquid ventilation. You might be wondering what liquid ventilation has to do with oscillations. First, some disclosures of commercial interests that I have, intellectual property. I do have to put a disclaimer because I do receive funding from the Department of Defense that these are my interpretations, conclusions, and they don't represent or are endorsed by the DoD or the Secretary of Defense. One big disclaimer I have to make is anesthesiologist. I have managed mechanical ventilation, probably thousands of patients in my career in the OR and the ICU. I have absolutely no clinical experience with liquid ventilation. So I am approaching this as a theorist and a modeler and somebody who is interested in mechanics and oscillatory impedance in general. Now, if you are not familiar with liquid ventilation, this is a very unique ventilator modality using liquid perfluorocarbons, often perfluorons shown here, as a carrier for oxygen and carbon dioxide rather than gaseous nitrogen. It comes in two broad flavors, total liquid ventilation, in which the lungs, the breathing circuit, the endotracheal tube are completely flooded with a PFC. And that obviously requires a special ventilator to do that. Often these ventilators are prototype ventilators designed by very specialized engineers. And then partial liquid ventilation, where the lungs are not completely flooded. There's an air-liquid interface, and you can use just conventional mechanical ventilation that you would see in the ICU. Now, there's a number of advantages of liquid ventilation over gas ventilation. For one thing, PFCs have very low surface tension. Compliance is improved. It's amazing how much compliance can be improved when you abolish the air-liquid interface. You can maintain lung recruitment. Because you've got an incompressible fluid in the air spaces, so you can't deaerate, the lung can't become atelectatic. So this reduces, obviously, mechanisms of ventilator-induced lung injury like atellect trauma. There are reports in very few clinical studies that have been done in neonates and adults reduced or improved oxygenation. There's also a lavage effect on the alveoli and the bronchi, where you can move out debris in the air spaces and the airways, and for unclear reasons, an anti-inflammatory effect. But there's some notable disadvantages over gas ventilation. It requires very complex delivery devices and transducers. This is a nice prototype that was developed at the University of Sherbrooke, I think. There's very limited clinical experience, as I've said, certainly in adults, maybe a little bit more in neonates. There's tremendous increased resistive and inertial loads that are required to move this fluid column in and out of the lungs. Hemodynamic impairments. Remember, you have to account for the hydrostatic weight of a perfluorocarbon in the lung, so that can impair venous return, cardiac output, that can lower blood pressure, etc. Lactic acidosis can develop for unclear reasons. And many of these perfluorocarbons are radio-opaque, especially if they've got fluorine or bromine ions on the carbon chain. So that will interfere with diagnostic X-ray imaging. You lose a very powerful diagnostic tool especially in the intensive care unit, maybe getting daily chest x-rays or CT scans. As a question of toxicity, these should be chemically and biologically inert. They're not metabolized by the kidneys or liver, but they are taken up by the reticular endothelial system. And for patients that have undergone liquid ventilation, they can stay resident in the body for years afterwards, actually. So, well, what does this have to do with oscillometry? So we're aware that many of the oscillometric indices have potential to provide very useful diagnostic information on lung structure, lung function, certainly with gas, but is there any role or even interpretability of assessing structure function relationships during liquid ventilation? So my motivation here is to determine how liquid ventilation influences global and regional lung mechanics required for adequate gas exchange. And specifically, I am interested in looking at the tidal volumes required to maintain eucapnia with liquid ventilation, the corresponding driving pressures or pressure amplitudes that need to do that, and that's important for the design of liquid ventilators. What are the indices like work of breathing and mechanical power? You know, these are mechanical power very much is used now as a predictor for ventilator-induced lung injury. It's thought that some liquid ventilation techniques result in a more homogeneous distribution of ventilation. I wanted to explore that with computational modeling. And then, of course, what this audience is probably most interested in is what are the effects on mechanical impedance. These kinds of questions are really impractical to answer experimentally. So this is a great application of forward computational modeling, which what I do here is rely on very detailed anatomic data, often obtained from CT imaging, to predict function from structure. With forward modeling, I can explore some mechanisms that underlie many different structure function relationships in the respiratory system, but I can do this over a wide range of different simulated pathophysiologic conditions, a wide range of different spatial and temporal scales. And this is very useful when it becomes impractical or cost prohibitive and sometimes even unethical to try to do this experimentally, either in animal models or even human patients. This is a little example of a computational model that my group did a few years ago, just looking at the distribution of strain and strain rate in a pig lung during mechanical ventilation. So how are we doing this? This is how we generate the forward computational model for liquid ventilation. We start out with a volumetric CT scan. This is a healthy adult male. And we segment out the central airway tree and the parenchyma so we can define a pleural surface boundary. And then the peripheral airways, we grow out to the pleural boundary with a space filling algorithm that was developed by Maren Taufai at the University of Auckland. She's been collaborating with us for a number of years. So we end up with a three-dimensional tree. This has over 60,000 airway segments, of which over 30,000 are terminal bronchi, and they'll be subtended by viscoelastic acini that I'll go into in a minute. So each of these airway segments and each acinus will have a defined mechanical impedance. And from this, we're able to obtain a frequency-dependent flow distribution throughout the lung. This was a simulated injured lung, so you can see a lot of heterogeneity in the distribution of tidal volume that comes in from the trachea. And then with some other gas transport models, we can solve numerically and some certain assumptions about the distribution of perfusion. We can determine the ventilation that's required to maintain eucapnic carbon dioxide elimination. So each airway segment of the model of over 60,000, we approximate as an ideal cylinder with longitudinal resistance and inertial elements that are based on the dimensions of the cylinder. There's also a gas compression compliance here, which we can obviously eliminate during liquid ventilation. The airway wall properties account for various distributions of soft tissues, and cartilaginous material, depending on what the generation is. And when we do liquid ventilation, we can simply eliminate the gas compression element. The longitudinal resistive and inertial elements are going to depend, of course, on the gas viscosity, the fluid viscosity, and the density. And these are the values that we've used for these simulations. You'll notice the tremendous increase in the perflubron compared to air, with the perflubron being about 124 times that of air for viscosity, and with density over 1,500 times. So we're going to be dealing with some pretty large viscous and inertial forces. Now, the acinus we model with a viscoelastic constant phase impedance. We have parameters for tissue damping and tissue elastance. The acinus is capable of de-recruitment if we want. We also have a gas compression compliance here. When we do liquid ventilation, remember, we abolish the air-liquid interface, and this is great for improving the compliance of the lung. So we adjust this elastance parameter H, depending on whether the lung is air-filled or fluid-filled. This is data that we obtained from a previous publication with saline-filled lungs. And of course, liquid ventilation, we're not de-recruiting, and we don't have any gas compression. There's some additional assumptions with the model. We have to account for different molecular diffusivities of CO2 in air compared to perfluorocarbon. The partial pressure concentration relationship for CO2 is going to be different. This is the effect of solubility if we're dealing with liquid ventilation. We make some assumptions about metabolism and define a particular CO2 production and oxygen consumption. These are set up to give a respiratory quotient of about 0.8. We assume a supine lung, supine patient. We didn't, for these simulations, didn't do any kind of prone ventilation. And then we have to account for the hydrostatic weight of the fluid. So there's gravitational distribution of alveolar and pleural pressures. And we simulated these based on a previous model that was published here in Respiration Physiology in 2000. So let's take a look first with gas ventilation. And I'm showing here the tidal volume that's required to maintain eucapnia over frequency range out to 3 Hertz, as well as the corresponding peak-to-peak airway pressures. So as you'd expect, tidal volume will decrease as we increase frequency to maintain eucapnia. And these are certainly in the range of what a healthy lung would be. The peak-to-peak pressures, about 2 centimeters of water. This may seem to be a little bit low to you, but I'll just point out this is subglottic impedance. So I have bypassed a ventilator breathing circuit. I bypassed the endotracheal tube, etc. Now, if you take a look at liquid ventilation, the tidal volume required to maintain eucapnia is right on top of what it would be for gas ventilation below 1 Hertz. There is some divergence after 1 Hertz or so, but you'll notice to deliver that tidal volume, of course, there's going to be much higher peak-to-peak airway pressures are going to be required, in order of magnitude more. That's probably not unexpected. The other indices it's interested in, the inspiratory work of breathing, as well as the inspiratory mechanical power. With the inspiratory work of breathing, this is the mathematical relationship for it, assuming pure sinusoidal variation in tidal volume. And I partition this into dissipative and reactive components. Dissipative, obviously, arising from resistive losses, and the reactive are going to arise from energy storage elements like compliance and inertia. And the inspiratory mechanical power is nothing but the time derivative of the work of breathing, which for a sine wave is just the inspiratory work of power multiplied by the frequency. This is sort of the classic graphical argument and presentation that you'll see to partition dissipative and reactive components of the work of breathing. So here's comparison liquid and gas ventilation for work of breathing and mechanical power. Again, you will notice that there's an order of magnitude increase for the worker breathing and the mechanical power over this frequency range up to 3 Hertz. This is again to maintain eucapnia in the model. But if we partition the worker breathing and mechanical power into dissipative and reactive components, some interesting things happen. This is dissipative and reactive percentages of worker breathing and mechanical power. They're identical because one is just the derivative of the other. And you'll notice for gas breathing, most of the worker breathing arises from reactive forces. All right, this wouldn't be unexpected because most of this is coming from the elasticity of the parenchymal tissues. But we flip when we move over to liquid ventilation, and the dominant component of the worker breathing and mechanical power become resistive. And this was a little surprising to me just because of the tremendous increase in the density of the perfluorocarbon compared to its viscosity. They both increase, but at least over this frequency range, resistive forces are going to dominate the worker breathing and the mechanical power. Now on to the impedance. Impedance during liquid ventilation has actually been measured in some very elegant studies by a group at the University of Sherbrooke. So if you're interested in what impedance looks like during total liquid ventilation, I can point you to these 2 studies from 2010 and 2012. These were done in neonatal lambs, but let's take a look at what the model does for us with an adult human. So
David,
this is resistance.
David, you're
Yep.
approaching 15 minutes, just to give you a
Okay.
heads up.
This is resistance and reactance with gas ventilation. Nothing surprising here. Frequency dependent drop below 1 Hertz with resistance, sort of an increase in resistance at higher frequencies as you encroach on the anti-resonance. There's a resonant frequency at about 3-4 Hertz. Now, I'm going to change the scales here. This is the same data, and I'm going to show resistance and reactance for liquid ventilation. And besides a tremendous increase in the values for resistance and elastance, you're going to note a lot of resonances and anti-resonances that are occurring with liquid ventilation. And this initially confused me, but my hypothesis was here that there are multiple resonances that are occurring as you have a transfer of energy of the inertia of the perfluorocarbon with different distribution of airway wall elasticities. So just to test this hypothesis, and this is a beauty of a forward model, I can make all the airways rigid, and I completely abolish all those resonances and anti-resonances. So just one last thing I'd like to show is the distribution of ventilation for gas in liquid ventilation, 3 different frequencies, gas on the left, liquid on the right. You'll notice there's much more heterogeneity for liquid ventilation compared to gas, more gravitational distribution of ventilation distribution at low frequency for gas. I'm showing the coefficients of variation for flow distribution here throughout the lungs. I'm only looking at the acini on the pleural surface here, but I can cut into the surface of the lung, go deeper into the lung, looking at the sagittal section. And you'll notice with gas or with liquid ventilation, besides being much more heterogeneous, the ventilation is mostly restricted to more central acini compared to acini out in the periphery. So just to sum up, despite some theoretic advantages of total liquid ventilation, there are some concerns that become apparent based on computational modeling. Certainly high mean airway or high oscillatory airway pressures to maintain gas exchange, tremendously increased worker breathing and mechanical power, increased heterogeneity of regional ventilation, And then, of course, the interpretability of oscillatory impedance becomes pretty obscure. But nonetheless, I hope that the forward modeling exercise has convinced you it can be an important tool for predicting physiology and therapeutic response to total liquid ventilation, and maybe even understanding the design specs for a liquid ventilator. So with that, just like to make some acknowledgements to my funding sources, and of course, Jake Herman and Marion Taufai, and I'm happy to take any questions.
Well, David, thank you. Again, an area that I have zero expertise on, so really informative for me. Fortunately, we have Jason, who has much more experience with these sorts of things, and in particular modeling. And I would just point out to those of you who are maybe new to oscillation mechanics, Jason's book on modeling is probably a must read. So I'd ask you to look it up and read it. Hopefully buy it and not download it off the internet. I don't know if the PDF is available, Jason, but over to you, please. And I'm really eager to hear how you handle this discussion.
Thanks for that plug, Ron. Yeah, well, first of all, Dave, this is your usual modeling tour de force. It's very impressive work. All the details and the technical aspects of the modeling. I'm pretty sure I don't know any other anesthesiologist or even clinician who can do this kind of thing. So the fact that you have both the clinical insight and the modeling capability is very valuable to the field. There's many aspects to this talk, and so I'm not going to go on at length. But one thing that did strike me as particularly interesting was those multiple resonances you got with the liquid ventilation that went away when you made the airway walls rigid, which, as you point out, implies that when the airway walls are not rigid, in other words, when they're physiologic, then you're going to be lateral oscillations of airway walls at various points in the airway tree. And I wonder whether the size of those oscillations might have some kind of implications. If you're doing multi-frequency HFO, high frequency oscillation using liquid, for example, could you have damaging amplitudes of the airway wall oscillations? Or might it even be therapeutic? Might be some benefit to that?
Yeah, that's a fantastic question. And where these resonances are occurring along the airway tree, we didn't explore, at least, for this little work. And how these may change with the amplitude of the oscillations, I can only speculate. But what I suspect is happening with this data, you have one resonance that could be occurring in more central airways, and then another resonance will pop up in more distal airways. But it's something that we could certainly look at when we look at regional or local resonant phenomena in the airway tree. But those are great points. I don't know.
But I'll just make one other point quickly, and then I'll throw it open. You talk about the work of breathing and the resistive and reactive power and so forth. And you and I both work in the field of acute lung injury as well, where this has become a very hot topic. And I think it bears some careful investigation or thought, because it seems to me that if you calculate reactive power, you are looking at energy that goes into the system during inspiration and comes right back at you during expiration and leaves nothing behind. I mean, that by definition is what it is. And a lot of the emphasis these days in the field has been, can we use mechanical power as some kind of an index of potential injury to the tissues? And I just think if it's the reactive power, the answer's got to be no, because you're basically pushing something in and it comes back out, leaving the system completely unchanged. It's presumably got to be the dissipative power that has the potential to do damage. Now, you're always going to get dissipative power because you have an airway resistance, but at some point, if it becomes too much, some of that dissipation could be reflected in microstructures breaking, in other words, tissue damage. And that, I think, is where you're going to start to get ventilator-induced lung injury implications and so forth. So
yeah,
Commentary about that.
That's very controversial right now. And what is the most important component of mechanical power and as a predictor of ventilator-induced lung injury? And I'm with you. I think it's mostly dissipative power. In these simulations, the dissipative power would be twice what I presented here because it's inspiration. So you count for exhalation. Anything that's reactive, you're going to recover back again. And with liquid ventilation, you obviously have much higher dissipative power, but is that due to the fact that you are dissipating energy in the parenchymal tissues and you're disrupting collagen and elastin fibers? Or is it just the dissipation that's required to move this heavy column of fluid back and forth through the airway tree? And is that injurious as well? So I can't really speak for that without doing the experiments and seeing what happens. So
yeah, great. Okay, well, terrific presentation, really great work. I'll leave it there, Ron. And
okay, well, we'll field a question maybe from Jeff, because I see his hand up,
Yeah.
and Cindy has one, so we'll do those two and then move on to the next
Yeah,
talk.
yeah.
So Jeff, over to you.
Thanks, David. Liquid ventilation's been around a long time. And I know other people have looked at it years ago. So but you're talking theoretical. So from the point of view of theoretical, in a fluorocarbon-filled lung, the lung recoil is going to be an order of magnitude less than in an air-filled lung. And the density, as you pointed out, is about 1,000 times or more compared to air. As a result, it's inconceivable that there's not flow limitation and airway collapse on expiration. Right? It's going to be flow limited almost all the time. So have you thought about that? That's not in your model at all. The model doesn't have airway collapse. So the prediction would be, theoretically, from the point of view of flow limitation, you get dynamic hyperinflation, a lot of heterogeneity, dynamic heterogeneity and hyperinflation, and flow limitation on expiration. So do you see any indications of that in real data where people have actually looked at pressure flow relationships?
I haven't, and I'm curious how you do get flow limitation because you've got incompressible fluids in the airway tree.
Well, compressibility has nothing to do with flow limitation. It doesn't come into it. It's airway collapse that causes flow limitation. I mean, these are things that are pretty well worked out.
But how can you collapse an airway if you've got incompressible fluid in? Well,
that's.
I'm talking about.
If you go back and look at all the work on flow limitation back in the 70s, 80s, and 90s, it's all pretty well worked out. And gas compression gas is really, really stiff compared to lung tissue. So it just, it's a minor correction. Flow limitation has really, you don't need compressibility at all. That's just not fundamental to expiratory flow limitation.
Jeff, that's a great point. Collapse. It's a great point, Jeff. I mean, I'm thinking, if you think in terms of wave speed, you can see you don't necessarily need to compress the airway, but you could have wave speed.
Right.
Flow,
right? Yeah. The wave speed flow limitation is mostly density dependent, and the compressibility just doesn't come into it at all. It's airway collapse that takes the role. I mean, in a jet nozzle in air, yeah, compressibility is important. Airway collapse plays that role in wave speed flow limitation.
If you can maintain lung volume at a certain level, and I suppose most of these liquid ventilators have to have a active exhalation to remove the perfluorocarbon.
Right.
So I wonder, depending on what the speed of that backstroke of the expiratory piston would be, can you mitigate any flow limitation effect?
Well, if you did it slowly enough, but in terms of the flow limitation air-filled, flow limitation liquid-filled is going to be thousands of times smaller. So I bet if you, there must be some literature on this. If you actually look at the flow volume loops, you showed an ellipse, but if you look at flow volume loops, they're not going to be elliptical. They're going to look very, very different on inspiration than on expiration.
Yeah, and these simulations are all done with pure sound.
Yeah. So I think that actually, based on what I understand about the problem, the flow limitation is the major part. It's the major part. So I think you might want to think about that. I don't know if Marin has the ability to model flow limitation. I've talked to her about this for years and years and years. And I don't know if she's gotten to the point to incorporate flow limitation in her model. If she does, you can put that in. She could put it in. I mean, enough is known about flow limitation now. I mean, it's been all worked out. She could put that in, but that's a huge leap from a linear system.
Oh, yeah. This model, these simulations are linear, certainly to generate the mechanical impedance spectra. And the airway dimensions are constant apart from the
Okay.
oscillation. Yeah.
If you want, you can call me sometime. I can give you some of the
I
literature
would
on
like to
this.
do that.
Yeah.
Actually, can I just
Cindy,
comment?
yeah, go ahead.
Hey, Jeff, that's a great insight. I hadn't thought about that. So what you're saying is that in the very small distal airways, you might reach maximal flow, which is way below what you'd like it to be if you were doing scaled macroscopic ventilation from the mouth. And so if that's the case, then I'm guessing that what you're doing when you're actually doing liquid ventilation is you're getting most of the ventilation is going into the more proximal lung and expanding the airways and coming right back out again. And the actual ventilation of the distal regions down to the alveolus is quite limited. Is that what you're saying?
Well, not during inspiration, there's no problem. There's no flow limitation on inspiration. So you'll be able to expand the periphery fine. The problem is you won't be able to get it out.
Okay, but at some point you're going to reach a steady state.
Oh yeah. But to do that, you'll have to. I mean, the two crucial things about flow limitation is that the driving pressure is lung recoil. That's what gets the liquid out. And in a liquid-filled lung, the lung recoil, instead of 30 centimeters of water or 10, it's 1 or less or 0. I mean, it gets really, really small. So you've got no driving pressure to get it out.
Yeah, no, I see what you're saying.
And the other is density. I mean, it's density dependent. Is when you look at the wave speed formula, density is the prefactor. So when you put in 1,000 times higher density, the flow rate's everything else being equal, the flow rate's going to go down by a factor of 1,000. So I think looking at flow limitation in liquid filled ventilation is really going to be, if you want to understand the mechanics of it, that's going to be, I think, central. Anyway, that's enough about that.
We should talk because I'm thinking there could be inspiratory flow limitation as well.
Okay, gentlemen, next year I'm going to have breakout rooms so we can continue to chat because the conversation is extremely important. And I'm glad that it's going to stimulate you guys into another collaboration. I'm looking forward to the paper that results from today's conversation. Okay, so thank you very much, Jason. Thank you very much, David. And I'm now going to hand the podium over to Irene Firion, who's from Mexico City. And Irene is going to talk to us about IOS, oscillation impulse oscillometry in tobacco, marijuana, and other inhaled substances. And I'm very pleased to have as the discussant Natalie Belosofa, who I've gotten to know through Chung Wei's group at the University of Toronto, where Natalie is currently a fellow, who seems to be taking very nicely to oscillation mechanics. So both of you welcome, and over to you, Irene. We're listening with interest.
Hello, everyone. Thank you so much for this opportunity. I'm a little nervous, especially because you are all experts and I'm just relearning on oscillometry. Well, like Dr. Ron said, my name is Ideri. I am a pulmonologist. I live in Mexico City and I work at INER. Our work is titled Respiratory Health and Quality of Life in Chronic Users of Marijuana. This protocol was implemented before some change to the law occurred in our country, such as the approval for the use of marijuana for recreational activities. It is important to note that marijuana is the most widely used drug in the world. The global prevalence in 2011 was 118, which means that almost 4% of the adult population consume marijuana. In our country, in Mexico, in 2016, in a national survey that was conducted, we have a prevalence of marijuana consuming that was reported in at 2.1%. There are many ways to consume marijuana, but smoking is the most common. The combustion produces many pollens similar of those produced by tobacco smoking. And comparing tobacco inhalation with marijuana inhalation, it's a bit different. In most cases, the inhalation technique is deeper and longer. So maybe it can be like some response for the difference that we will be that we've seen in the results that I will show in the next slides. And systematic reviews have found higher risk of chronic bronchitis, respiratory symptoms, but there is not clear generation of other lung diseases, for example, for COPD, emphysema, lung cancer, or some cardiovascular diseases. And maybe this is because one of the difficulties that we have so is that it's difficult to separate the effects of tobacco smoking from those of marijuana smoking, because many of these consumers coexist. It's like both consume tobacco and both and also consume marijuana. So maybe it's difficult to separate these effects that makes marijuana alone. Our objective was to evaluate the impact of inhaled cannabis smoke on the respiratory system, including clinical manifestation and lung function. The protocol was carried out between 2016 and 2018. A public institutions that help drug users, that's called Joe Integration Center, refer the patients to our hospital, the Pulmonary Function Test Laboratory of INER. And here the definition of chronic marijuana consumption was marijuana use in the last 5 years, or marijuana, the use of marijuana more than 100 times in the last year. In our hospital at the Pulmonary Function Test Laboratory, we performed a questionnaire that was like all the respiratory symptoms, the expositions, and we made a spirometry, oscillometry, and the LCO. Like I said before, a substantial proportion of the individuals were not only users of marijuana, so we have to make 3 groups in our protocol. The ones that were only users of marijuana, another group that was marijuana and tobacco users, and the last that was multiple user, that was tobacco, marijuana, cocaine, ecstasies, and other drugs. So here we can see the demographic characteristic of our groups. And as you can see, we have that the multiple users were younger than the other, but also we have in all the groups younger people, but the multiple users were the youngest. More than with the male sex predominant in all the groups. As you can see, more than 80% were male. And also one of the most important things is that more than the 60% of our population consume daily marijuana in the last year. So the consuming of marijuana was really high. Also, with the different median years of consuming, marijuana users had the highest median with 9 years of use. As you can see, the group of marijuana plus tobacco have a median of 3 years of consuming this drug. Give me 1 second. Yeah. Okay. One of the other things that it's important is that marijuana users report more lung disease, 20%, than the other two groups. And for other comorbidities, that is rheumatology disease, diabetes, and cardiovascular disease, the group of multiple users have the highest report in 33%. When we analyze the respiratory symptoms, but we group more than 2 respiratory symptoms, we can see that almost 1/3 of the participants report more than 2 respiratory symptoms. So this is important, and it's much of the same that is reported in the literature. Here we can see the results of the spirometry. In the spirometry results show us among the groups, the multiple users had the higher percentage of predict, also in FB1 and FBC. As you can see, multiple users had a percentage of predict of FB1 in 109, and for FBC, 114. For DLCO, there were no difference between groups. We also have almost normal values, but when we analyze really the function diagnosed, we found that 38% of the people that were in the group of marijuana plus tobacco users had an obstructive spirometry in the prebronchodilator. But after the bronchodilator, only 17% remain with an obstructive pattern. In the other hand, when we analyze the function diagnostic in the LCO, we can see that the LCO was increased in 40% of the patients who use only marijuana. Now we are going to see what happened in oscillometry. Here, for comparing the 3 groups, there were no difference, but here we can see that resistance are similar between groups. When you saw here 0.226, 0.28, and 0.25, but we noticed the difference after we put the bronchodilator. So with almost 50% less resistance in marijuana users, and practically we don't have any change in the multiple users. What happened with resistance on 20 Hertz? Here it's more like the last slide, where we have the resistance very similar between the 3 groups. And after we put this bronchodilator, we can see that, again, we have less resistance, most in the group of marijuana users. Also, when we see this in the group of marijuana plus tobacco. And again, we don't see any change in the group of multiple users. When we analyze the delta of resistance, again, we don't have any difference between the 3 groups, but we have difference after bronchodilator in marijuana users, and these groups of marijuana users and marijuana plus tobacco. So it's more the same like the 2 slides that I have shown you. In the case of reactants, in the post-bronchodilator, there are less negative values, as you can see. And again, in the group of marijuana users and marijuana plus tobacco, we can see the same effect. Again, when we compare the 3 groups, we don't have any difference between these 3 groups, but the difference that we can see is when we have the analysis between the pre-bronchodilator and the post-bronchodilator in these patients. what happens when we analyze reactance area? Again, there was no difference between the three groups, but here, as we can see, in all the groups, now in the multi-producers, we can see a statistical difference after the use of a bronchodilator. And now in the multiple users, we can see the biggest change with this difference. So just for finish this this presentation, until now we don't find difference between the three groups. It's important to say that our groups were with less people. We don't have much number of people to compare, but with the people that we have, we don't found any difference between the three groups. The findings, the positive findings that we can share is that there was difference before the administration of the bronchodilator in resistance and reactance, almost in the group of marijuana users and also in the marijuana plus tobacco users. And one of the things that also we have shared is that reactance area decreased in all groups after the use of a bronchodilator, but the greatest change was with the multiple users. So this maybe it can be a question we can answer in the next years. Because I was searching about it was a minimal clinical important difference between these parameters, and know that this can be like like a difference between the symptoms or something that the patient can clinical share us to be like something better with that kind of symptoms. So perhaps it will be important to analyze what is the minimal clinical importance difference in oscillometry. So with this, I am finished. So thank you so much for all the people that was working with us in this protocol. But much with Miss Laura Gochicoa. So now I'm finished. Thank you so much.
Riri, thank you very, very much for a fabulous presentation. And you're really bringing up a point that we've been struggling with on the task force. What is the differences between pre and post bronchodilators in the various derived parameters of oscillation mechanics? So I'm going to turn the floor over to Natalie to tackle this discussion, but I hope that if Shannon Simpson and Dave Kaminsky are on the call, they'll join in. And Cindy, if you're still there, I'd like your 2 cents worth, because as I said, we're struggling on the task force with these issues right now. So Natalie, over to you, please.
Hi, Riri. Thank you for that excellent talk. I actually just was curious. So you didn't find a difference between the 3 groups. It would be interesting to see a comparison to just pure tobacco smokers and I guess a comparison to non-smokers. And I'm just wondering if you had any plans to do that or any, I guess, those comparison groups.
Yes, we only have a group of healthy people, but we only have the spirometry data and the clinical data, but not with oscillometry. So right. Now what we are going to, the next step is to compare with health people that doing this oscillometry, but also only tobacco users. To know if there is any difference between one of that groups. But yes, this is one of the next steps. Also, the protocol was included at high resolution CT, but we have also some problems because we only have the qualitative analysis. So we don't have like the long volume specific for quantify or to know about small airways or something like that. But we have that information, but we have to analyze them.
Yeah, that would be really interesting to see that data when that becomes available. I think that's going to be really good. So we've got a question from Charles Irvin.
Yeah, really nice talk, and I'm going to echo something that's already been said. And one of the issues that you have is you don't have a positive and negative control to make sure that you're measuring it, things. And so I really like the idea of looking at tobacco smokers, but I think the other thing I would do is look at the acute effects of cigarette smoking just to make sure that you can detect something. But as I recall, and this is a very long time ago, it takes me way back, marijuana, THC is a bronchodilator, weak, okay? I remember the kids would come up to me in class and encourage me to legalize it back in the 70s as a treatment for their asthma, which was like crazy. But you're not really seeing any bronchodilation effect. But I was wondering, what's the time frame between your measurements and the last time they were imbibing?
Okay. Yes, there were some reports that marijuana have some bronchodilator effects. But then there were some other that said that depends of the kind of the marijuana, but we don't know yet. Yes, these people have at least 20 hours without consuming marijuana or tobacco.
Okay. So that's likely it. But you really raise another interesting point, which is true about tobacco too, and that is the marijuana you're looking at is legal, right, in Mexico?
Right now, yes,
Yeah.
but this is in this year.
Yeah, well, the marijuana that I recall from my misspent youth was illegal and it was laced with all kinds of crazy things. So,
yes.
And the as I understand it, and I have no personal experience now, but that the legal stuff is also very potent, is it not?
Yes. In fact, the protocol was made when we don't have this legal thing. So that's one of the limitations also that we have in our protocol. But maybe now that it's legal for recreational activities, maybe we can follow these people or include another users.
And the nice thing is it's now being analyzed by the commercial folks because they want to use it as an advertising thing.
I wonder if I could ask, how common is vaping in Mexico?
Well, I think we have a problem because it is very common when you go to the streets. You see a lot of people that is vaping in universities, high school, but with the law, it is not permitted. But it's you can buy in any place that you go, buy it online, so it is very common. But one of the problem is that like physicians, we are not asking about the expose of the vaping. So I think that most of the information we have, it's with some problems or are not really true because we are not asking about the exposure of vaping. So we are working about always asking for the people, not only if they are exposed to tobacco or another drugs, also if they are have some exposure to vape. But yes, we have report of some patients with EVAL.
Could I just clarify something in one of your slides? You mentioned the frequency of consuming, and that kind of was given as a percentage. Is that sort of percentage of days on which they would use marijuana, or yeah, just wanted to check what that. Just in terms of quantifying their exposure.
We made like a questionnaire about if they consume daily marijuana and like approach of like it will similar like a cigarette. So that's the approach we have to know how much marijuana they are consuming. So we ask about how many cigarettes, like it will be like a tobacco, they are consuming. So more than 60% of the patients consume more than one cigarette daily.
Okay, yep, I understand.
Okay, well, I don't see any other questions out there, so maybe we minimize the overtime. We already have at least a 10-minute deficit ahead of us. We'll move on to the next stop. Thank you very, very much, Natalie and Iriri. Just Iriri, one other plug. If you guys are looking for imaging in terms of quantitative approaches, you can check out the chest imaging platform out of the Brigham. They have a software slicer that has a suite on it for doing quantitative CAT scanning. It's relatively intuitive and straightforward, and I would give a shout out to Raul Estebar, who's quite willing to work with people to get them up and running with this. So that might be something of use to you. Okay, so the next talk is going to be from Iriri's colleague, Laura Gachikova, also from Mexico City. And Laura is going to talk to us factors related with iOS values in a cohort of over 530 post-COVID-19 patients after 2 to 42 weeks of follow-up. Certainly of great interest to many of us on the call after all the clinical experiences we've gone through. And I'm super pleased to have as a discussant Deborah Asiag, who is from McGill, and Debbie is one of our junior attendings who's now running our interstitial lung disease clinic and has managed to get funding to deploy oscillation mechanics in her interstitial lung patients. So I think we can expect to see some interesting data coming out of Deborah in the coming year and years. So over to you, Laura, and then on to you, Deborah. Thank you very much, both.
Okay, good morning, everybody, and thank you very much, Dr. Ron, for all your enthusiasm in this summer oscillometry seminar. So I'm going to present this study about the factors related with oscillometry in patients that were recovered from COVID-19. These are my conflict of interest. So as we all know, this coronavirus disease continues to be a global public health problem, which has affected thousands of families around the world. Right now in Mexico, we are in our third wave, and it's very likely that more waves will come in the future. So unfortunately, this disease has affected, well, men and women, but most of them, at least in Mexico, are in the productive life. So this is a very important issue for us. So at the beginning of the pandemic, pulmonary function laboratories were forced to stop. And in many places, such as in our institution, we had the need to give care to patients with COVID and to those who recover from this terrible disease. So we made guidelines that could allow us to perform respiratory function tests in the same standardized manner, but also with the lowest possible risk. So the first publications found in the literature show us that individuals recovering from COVID has as the main sequel some restrictive patterns and also some altered diffusion capacity, but interesting, only few patients show obstructive patterns. In these longitudinal studies also have shown that in some patients, these restricted patterns and the altered diffusion capacity can improve up to 12 months after presenting the disease. And as in other assessment centers, we have found the same results, low volumes and low capacities. And most of our patients with the same prevalence of gas exchange impairment, especially in those who receive invasive mechanical assistance to ventilation. And although many of these patients improve in these parameters, in the longitudinal follow-ups, other tests such as the 6-minute walking test do not improve substantially over the time. So sometimes I think we are limited to traditional tests. And from the point of view of respiratory mechanics, there are other studies such as oscillometry that could give us a broader view of the pathophysiology of the disease. And when we think about on the damage that the coronavirus causes to the lungs, it is complex to imagine that the respiratory mechanics is not affected in a greater degree. And thinking about it is that we consider performing oscillometry in these patients. As we know, when we perform an oscillometry, the measurements of the resistance at low frequencies such as R5 reflect the resistance throughout the airway or the respiratory system, and the high frequencies represent what happens in the central airway. So it is logical to think that the difference between R5 and R20 will be talking about what is happening in peripheral airway. We also know that the central airways offers around 80% of airway resistance, while the peripheral airway offers around 50 to 20% of this resistance. Some authors have proposed that the difference between R5 minus R20 greater than 0.07 or a reactance area above 0.35 kilopascal per liter could be observed when there is a damage in the small airway. Or if we found that the small airway is offering a resistance greater than 25%, we can also think in peripheral airway disease. So the aim of this study was to describe the lung mechanics in post-COVID-19 adults and to describe factors related with oscillometry, including the current symptoms, days with tracheal intubation, days as inpatient, and time from symptom onset. So this was a prospective core study approved by the institution scientific committee, and it was performed from May 2020 to May 2021 in adult subjects who suffer from COVID-19 and who were invited to perform pulmonary function tests, including oscillometry at the Department of Respiratory Physiology at the National Institute of Respiratory Disease located in Mexico City. The pulmonary function tests were performed according to the international guidelines in a master screen PFT and a master screen body PFT. And this was the analysis I am going to present. So in our results, these are the characteristics of the study population. And as you can see, the time from symptoms onset to the PFTs were around 4 months. Most of the population were hospitalized for around 16 days, and almost half of them received invasive mechanical ventilation. These are the current symptoms presented at the day of the PFTs. And as you can see, fatigue and myalgias were the predominant symptoms, and 60% of the participants continued with dyspnea at the time of the study. These are the factors associated with lung function tests in males, post-COVID patients, and these are the factors associated with this lung function test. And as you can see, dyspnea was highly associated with the results in oscillometry. These are the factors, but in females. And as you can appreciate, dyspnea was associated mainly with the reactance area. So these are the results of oscillometry and spirometry in males and females. And what stands out is that only 1% of the participants had a functional diagnosis of obstruction by spirometry. In the oscillometry, the median value for R5 minus R20 was 0.08. That is above 0.07 cutoff point, and the median for small airway resistance was around 25 24%. In this figure, you can see the number of individuals in whom the R5 minus R20 was above this point of cutoff point of 0.07. And in here, we can see those subjects where the resistance that were given by small airways was above 25%. And in this last figure, you can see that most of our participants had a reactance area above 0.35 kilopascal per liter. So when we analyze these numbers together, we can see that around 79% of those whose spirometry was interpreted as normal actually could have a small airway disease measured by oscillometry. So in conclusion, in an adult population, results of pulmonary function tests performed around 4 months after suffering from COVID-19 were associated with some clinical factors, especially dyspnea in males. Current dyspnea was related to data just suggestive of small airway disease, such as high R5 minus R20 or the resistance offered by small airways. In females, dyspnea was associated with large reactance area. So by oscillometry, it seems that these individuals have small airway disease and that spirometry may not be sensitive enough to detect mechanical lung function abnormalities in this post-COVID-19 period. So thank you very much for your attention.
Okay, Laura, thank you very, very much. That was a simply great talk of tremendous interest to us all as I prefaced your presentation. And please, Deborah, take over the podium for the discussion, and we can open the floor up to everybody after you've had a few comments and questions yourself.
Thank you, Ron. Laura, that was such an interesting talk, and such a big population of post-COVID patients. 530 patients is quite a high number, so congratulations to you for doing this work. Do you have any data on what their chest imaging looks like? Do you have any, did you look at their chest X-ray or their CT scans to see what does the disease look like? So we think of post-COVID disease, especially 4 months out, which is when you did the test, as more of a fibrotic kind of disease, more of an interstitial fibrotic disease. So in those patients, I wouldn't expect to see such amount of airways disease, even small airways disease. So I'm quite surprised by your findings. Do you have any information on that?
Thank you, Deborah. Yes, well, we have CT scan, not from all the patients, but unfortunately, most of these CT scans were simple. I mean, we don't have this high resolution tomography or inspiration and expiration. And our results by the radiological findings are not different from what we are finding in literature, like these bands and all what we have seen. So I think some of the next steps we have to give is to have this high resolution tomography to see what is going on also in these patients.
Yeah, I mean, I think that'll be the really next important steps. Some people think, you know, if you look at the pathology in patients with COVID, they have a lot of organizing pneumonia, and organizing pneumonia is plugs of fibroblastic tissue within the small airways. So possibly that explains some of your findings. It would be really interesting to look at imaging. I think we have a question from Grace Paraga. Grace, you can go ahead.
Yeah, thank you. I hope you can hear me okay. That was a terrific talk, and I just want to say that we have a smaller study similar to your study in Mexico with the same time frame, albeit in people in southwestern Ontario, a small group of patients, and we do see evidence of small airways disease and pulmonary vascular disease, but no evidence at this point. I'd say 12 weeks, 6 months, and 1 year post of fibrosis happening. So we are now pushing that information back to the clinic And these patients are being treated for small airways disease with Symbicort. Now, based on the oscillometry and the CT findings and the MRI findings of ventilation heterogeneity. So we're seeing very similar things, which is kind of a sanity check for us here in Canada.
And Grace, if I may ask, are you testing those patients after the Symbicort to see if they're improving?
Yeah, that's what's ongoing. And as you probably know, it's a challenge to convince people, even when they don't feel well, to take Symbicort. But the imaging findings and the oscillometry findings are really helping us show people that the Symbicort is really what is needed right now. And we describe it as a post-COVID asthma to try and make people understand that it's a good thing to do. We don't have any, we don't have sufficient evidence now to show that the Symbicort is resolving the small airways disease. And, you know, there is the natural changes over time in these patients. So we're using it more as an acute care lever to say, look, you know, we have evidence of this and this will help.
Grace, I would just caution you that that's a great initiative. With the Symbicort, you have to pay close attention that they've got really good inspiratory flow to fractionate the powder into the ultrafine component that's going to go to the small airways. And I would wonder what made you go with Symbicort rather than a known ultrafine and solutions such as the beclomethasone in solution or the cyclicinide in Canada as Qvar and Alvesco respectively.
I can't really comment on that because that's not my decision. We're just doing the imaging and the research, and we're pushing the results to the clinic. The clinic decision in our environment tends towards Symbicort PRN. Yeah, I take your point, but that's out of my wheelhouse for sure.
Thank you.
Leonard, you want to go ahead with your question?
Hi, thank you very much. Thank you, Laura. It was very interesting and a lot of information. I need to go back and look at this recording once it's published to capture it all. So maybe some of my things are already there. I essentially got two questions because I've seen some preliminary data from other sources using oscillometry already, and it seems to match essentially what you seem to suggest, that there's a big element of what seems to be restrictive disease. So that sort of begs the question about the small airways involvement and how much of a fraction of the disease is really small airways and how much is restricted. And then tacking on to that, has anybody looked at reversibility with bronchodilators in these cases, and is that of any effect whatsoever?
Oh, thank you, Dr. Leonard. Yes, we have the numbers of post-bronchodilator, but I didn't show it here. By spirometry, we didn't find any, or well, a lot of changes, but I have to look at the results of oscillometry, and I will let you know. But we are also planning to do some prospective studies looking for these patients that we find this small airway disease by oscillometry. Probably we can give, perform an, how you say, cardiopulmonary exercise test or some exercise tests where we can look if these patients are having volume, attracting volume, I mean, or if they start to have more residual volume or a less inspiratory capacity, just to see if we are correct. And yes, I am agree with Dr. Grace that, well, if we think about in children that has these low values of surfactant and they receive also steroids, they improve. We can think the same thing here with these patients. So we are also expecting for those studies.
Okay. Yeah, because I think you had some sort of index for small airways involvement there that I found kind of intriguing, but also because in the face of a restricted disease being more of a longer term issue maybe. So is this something that is a continuum that you go from small airways to restrictive, or do you have everything at the end of the day? Do you have any ideas about that?
Yes, we will try to do that. And so those will be our next steps for this study.
Yeah, longitudinal, this will be an interesting disease to follow. Thank you.
Yes.
If there are no other questions, Ron, I give the floor back to you.
Okay, well, thank you very much, Deborah. Thank you very much, Laura. It's now a great pleasure to introduce a group which is very dear to me, and that's the Greater Grace Paraga lung imaging group that seems to be fertilizing many centers in Canada. Sarah Svenningen is coming from McMaster, where she's doing great work after having trained with Grace. They've certainly taught me a lot about ventilatory heterogeneity and provided great teaching materials for talking to general practitioners about this concept as we go forward, exploring the potential utility of oscillometry as a community point of care test in the evaluation of lung disease. So Sarah, I'll give the podium over to you, and we look forward to Grace kicking off the discussion afterwards. And please, my apologies for the lateness, but this is a recurring issue with these seminars. I will not end the recording. You guys have as much time as you want. And happily, generally 80% of folks will stay on the call after 9 o'clock, and I'm sure that won't be different today. So take it away, Sarah.
Thank you very much, Ron. You should be able to see my slides.
Indeed, we can.
All right, and just a quick disclaimer, my Wi-Fi modem was appears to be knocked out this morning from an early morning storm, so I'm relying on my iPhone data for this connection. So I'm not going to turn on my video, and fingers crossed we don't have any troubles. So I do apologize for that. But anyways, it's an absolute pleasure to have participated in this seminar series this summer, and I've really learned a great deal from all of you. So thank you very much. And we've started to integrate oscillometry measurements into the workup of severe asthma patients at the Firestone Institute for Respiratory Health. And I've taken quite an interest in these measurements and the wealth of information that can be described from them, particularly from a research perspective. And while whole breath analysis of respiratory system resistance and reactance has really been the focus of this seminar series this summer, we've really been and have been extensively studied in asthma. I think we would all agree that one of the advantages of respiratory oscillometry is that we can separately evaluate these measurements during both the inspiratory and expiratory phases of tidal breathing. And due to the dynamic changes in flow, in lung volume, and luminary that occur during breathing, it isn't at all surprising that respiratory mechanics may vary quite markedly within the breathing cycle, particularly in asthma. And in adults, previous data has shown that total respiratory system greater than in healthy.
Sarah, could you back up about 1 minute in your presentation because we lost you?
Oh dear, okay. Can you hear me now?
Yes.
Okay. So I'll just, I'm not sure where I ended, but due to the dynamic changes in flow and lung volume and also luminaria that occur during tidal breathing, it isn't at all surprising that respiratory mechanics may vary quite markedly during the breathing cycle. And in adults with severe asthma, there's been previous work in this area. Total respiratory resistance, measured as resistance at 5 Hertz, has been shown to be greater during expiration than inspiration. And reactance was shown to not be different during inspiration and expiration. And the magnitude of these differences in resistance were greater than those in healthy controls. So I think there's really a need to better understand and more deeply look at these within breath differences in resistance and reactance in severe asthma, particularly to understand their potential clinical relevance and whether these differences should be taken into account alongside full breath measurements. And just, can you confirm that you can still hear me?
Yes, we lost you for just a second, so continue from where you were.
Okay, great. So our objective was in adults with severe asthma to better understand these within breath differences that have been reported in respiratory system resistance and reactance by evaluating the response to bronchodilator therapy and the relationship with asthma control and ventilation heterogeneity. So to do this, we undertook a retrospective analysis of healthy controls in severe asthmatics who had performed same-day respiratory oscillometry, xenon MRI, and spirometry. And we performed these assessments pre and post bronchodilator in severe asthmatics, all of whom withheld their short-acting beta agonists for more than 6 hours, their LABA for more than 12, and their LAMAs for more than 24 hours. And respiratory oscillometry was performed during tidal breathing. We stuck to the guidelines, and we used the Thoracis tremoflow system to obtain both whole breath, inspiratory, and expiratory respiratory system resistance and reactance measures. And our data set consisted of 17 healthy controls and 47 patients with severe asthma. You can see here that the asthmatics were slightly older. They had a higher BMI than the healthy controls, and 51% of them were obese, and 72% were uncontrolled at the time of study using the ACQ threshold of greater than 1.5. And if we look at the medication usage, we can see that 38% of the asthmatics were OCS dependent, and 32% were being treated with a monoclonal antibody for their asthma. And this table summarizes the whole breath respiratory oscillometry data, which isn't the focus of this talk, but these results agree quite well with previously published work. As we would expect, resistance at 5 hertz, resistance at 19 hertz, and the frequency dependence of resistance were all greater in our asthmatics compared to our healthy controls. And in our asthmatic group, these measures were all decreased with bronchodilator. The reactance at 5 hertz was more negative in our asthmatic group compared to our healthy controls. And again, the magnitude of this was decreased with bronchodilator. Okay, so diving into the within breath oscillometry data, this slide summarizes the total, the central, and the peripheral airways resistance as we estimate by resistance at the 5 hertz, resistance at 19 hertz, and the frequency dependence of resistance respectively. And I'm showing here both the inspiratory and the expiratory phases of tidal breathing with healthy controls in maroon and our severe asthmatic group shown in black. And you can see that our 5, our 19, and the frequency dependence of resistance differ during inspiration and expiration in both of our groups. For the healthy controls, we consistently observed that these measurements were all greater during expiration than inspiration. And for our asthmatic group, we saw that we observed that our 5 and the frequency dependence of resistance were greater during expiration than inspiration. But what was quite interesting was that resistance at 19 hertz was greater during inspiration than expiration. And as I mentioned, all of these asthmatics repeated oscillometry following bronchodilator inhalation. And as we would expect, our 5, our 19, and the frequency dependence of resistance were all decreased during both the inspiratory and expiratory phases with bronchodilator. And if we revisit the difference between inspiration and expiration, now following bronchodilator, we can see that our 5 and the frequency dependence of resistance remained greater during expiration than inspiration, but this difference in central airways resistance was no longer statistically significant. And if we plot this data in another way, here displaying the within breath delta, or the difference between the inspiratory and expiratory resistance, we can more clearly appreciate these within breath differences and how they compare between our healthy and our severe asthma groups. Again, I'm showing here the healthy group in maroon, and the black indicates our asthmatic group. The solid black bar is pre-bronchodilator and the open black bar is post-bronchodilator. And comparing the magnitude of these within breath differences that were described on the previous slide, we observed that the within breath difference in both R19 and the frequency dependence of resistance was greater in our asthmatic group, both pre and post bronchodilator. And focusing in on the bronchodilator effects observed in our asthma group, bronchodilation significantly reduced the within breath difference in R19, but not the within breath difference in the frequency dependence of resistance. And what about reactance at 5 Hertz? For healthy controls, reactance at 5 Hertz was less negative at expiration than inspiration. And for the severe asthmatics, we didn't observe a difference between the inspiratory and expiratory phases of tidal breathing with respect to reactance. But you will certainly appreciate the variability between asthmatics, with some of these patients having much more negative reactance at expiration than inspiration, which we didn't observe in our healthy control population. And following bronchodilator inhalation, reactance at 5 Hertz during both inhalation and exhalation became less negative. And again, displaying the within breath delta, or difference between the inspiratory and expiratory phases of reactance, we can see that as a whole, the magnitude of these within breath differences were not different between our asthmatic and our control groups. So I'll take a moment now to summarize the within breath differences. Central and peripheral airways resistance, which was estimated by resistance at 19 Hertz and the frequency dependence of resistance respectively, differed during inhalation, inspiration and expiration in severe asthma, and the magnitude of these within breath differences were greater than what was observed in healthy controls. Central airways resistance was greater during inspiration, whereas peripheral airways resistance was greater during expiration. And following bronchodilator inhalation, this within breath difference in central airways resistance was reduced. However, the within breath differences in the frequency dependence of resistance remained greater during expiration. And with respect to reactance at 5 Hertz, which we interpret as elasticity or lung de-recruitment and airway closure, this was not different during the inspiratory and expiratory phases of tidal breathing in severe asthma, but there was a high degree of intersubject variability. So as a logical next step, we wanted to try and understand if these within breath differences are clinically relevant in patients with severe asthma. And to do this, we evaluated the relationship of resistance and reactance measurements with asthma control, which again, we quantified as the 5-item asthma control questionnaire. And for this analysis, I've included both the whole breath and the within breath measurements to try to get a better understanding of the potential importance of considering these within breath measurements over the more widely used whole breath measurements. So I'm showing here Spearman correlation analysis with results displayed according to their R value, the most negative R value on the left of the slide and the most positive R value on the right. And what we observed was that pre-bronchodilator only, greater within breath differences in the frequency dependence of resistance and resistance at 19 hertz were associated with worse asthma control. And you'll also notice, however, that there were significant correlations found with a slightly higher R value for whole breath reactants at 5 hertz and AX, both of which retain their clinical significance after bronchodilator. We're also uniquely positioned to evaluate relationships with ventilation defects, quantified as the ventilation defect percent derived from hyperpolarized xenon MRI. And we did this analysis in a subset of 25 severe asthmatics who had completed both oscillometry and xenon MRI in the same study visit. And again, here I'm highlighting relationships between within breath differences in resistance and reactance in the MRI PDP. And you can see that greater within breath differences in the frequency dependence of resistance and R19 were associated significantly with ventilation abnormalities that we quantified by MRI. And to give a few examples of these, the ventilation patterns in some of these patients, here I'm showing hyperpolarized xenon MRI coronal slices arranged from posterior to anterior in a representative male with severe asthma. And you can see here that ventilation is normal and homogeneous in this severe asthmatic who had very minimal within breath differences in resistance. And in contrast, these are two asthmatics with significant ventilation abnormalities and heterogeneous ventilation, both of whom had quite large within breath differences in resistance. So to summarize these relationships that may speak to the potential clinical relevance of within breath differences, greater within breath differences in central airways resistance and peripheral airways resistance were associated with worse asthma control and with greater ventilation heterogeneity. And to conclude and lead us into discussion of these observations, respiratory oscillometry detected differences in central and peripheral airways resistance during tidal breathing in severe asthma. And these inspiratory-expiratory differences were reduced following bronchodilator inhalation. And of particular interest is this persisting within breath difference in the frequency dependence of resistance that seems to be associated with worse asthma control and ventilation heterogeneity. So I'll end there by thanking the team who has greatly contributed to this work, particularly those that I've highlighted in blue, Dr. Per Nair, who is managing these patients clinically, Ron Dandran for his expertise and insight in oscillometry, and Melanie Karsgaard. So thank you very much.
Well, Sarah, thank you for an absolutely superb talk. You've carefully documented a lot of information that will give us much to ponder as we leave the seminar. Certainly, it speaks to the heterogeneity of these severe asthmatic patients, which is the challenge that we face in everyday practice. There is not one size fits all treatment, and clearly there is a pathophysiology behind all that. So Grace, I do look forward to how you lead off this discussion. I would ask you to draw out Zoltan Antosh at some point if he doesn't come forward spontaneously, because he's certainly been doing a lot of thinking about within breath and intra-breath lung mechanics, as have a number of others out there. So I'm sure this is going to be just a great discussion. So please take it away, Grace.
Great. Thanks very much, Sarah. I just want to make a disclaimer. Ron was very effusive in his praise. Dr. Svenningsson is independent, and she has single-handedly turned McMaster University into a pulmonary functional imaging powerhouse. And I think this is the first time I've seen this work. And I think what struck me is the intricacies of the findings and how well phenotyped the patients are. So I have a lot of confidence in your results. And, you know, maybe I misunderstood, but to me, it seems like you're seeing greater central airway resistance during inspiration as compared to expiration. And that's in severe asthma, and that's not what you're seeing in healthy, so-called healthy controls. I wonder, Sarah, can you walk us through what you think are the sort of pathophysiological constructs or mechanisms that can explain this?
Yeah, thank you very much, Grace, for that question. I suspected that one for sure, and I've been thinking about this quite a lot, and I hope to hear some thoughts and some insights from the attendees who have studied this in a lot more detail. And at the moment, really what we're trying to do is better understand this observation by looking in detail at the time course plots of flow and resistance during that 30-second acquisition. And what that increase in R19 at inspiration appears to be driven at the transition between expiration and inspiration. And then it falls off quite quickly. And in a lot of these severe asthmatics who had been withholding their medications quite extensively, I wouldn't say a lot of them were actually in having some trouble with their breathing at this time because they had done a stringent withhold of their medication. So that may have contributed as well. So I'm suspecting that flow was quite turbulent at that transition point, which may have contributed to that high resistance in the central airways assessed by R19.
Great. I have a number of questions here across my panel, and I'm sorry if I'm a little bit biased here, but Peter Calverley, Cindy Tamarin, Jeff Maxim, and Zoltan Hantos. I'll start with Peter because you're the first one on my screen.
Yes, obviously the same configuration as I have, Grace. What a lovely way to end this series of seminars, because there's an enormous amount of excitement in this data, and it shows just how powerful a technique this can be in exploring things for the future, and really well presented, very, very interesting. You can imagine what I'm going to say, so I'll say it. And that is, I'm fascinated by actually the reactance data here. The resistance data are very interesting, and it's clear to me that resistance in asthma, including severe asthma, is a really very informative variable in a way it isn't in the disease I know best, which is COPD. But also the reactance data are intriguing. And I wondered whether you're in a position to try and partition either groups of breaths or better single breaths into those who had a significant, let's say 2.5 centimeters of water per liter per second difference in within breath reactance, because that does correlate robustly, fairly robustly anyway, with the presence of expiratory flow limitation. And I just wonder if some of those people who showed the variability in reactance are actually persistently flow limited at rest. And it seems to us, at least looking at the COPD rather than the severe asthma literature, that those people behave somewhat differently, are often more symptomatic and have additional problems. And just one other thought, in terms of your analyzing the clinical side of things, it might be interesting to know how much of some of the numbers fed into a multivariable regression, which looked at explanatory variables like complex endpoints like the ACQ, where it means some of the variance is actually explained by the resistance changes that you've come up with. This is very exciting stuff, and I look forward to seeing it in more detail.
Yeah, thank you very much. And we're certainly thinking about, those patients, as you mentioned, where there's a large difference and we see a significant drop in reactance during the expiratory phase, those asthmatics having a component of expiratory flow limitation. And to be able to partition those out would certainly be quite interesting and something that we can do with this data. So thank you.
Great. If it's okay, we'll move over to Cindy. We have another new hand. Charles Irvin is going to speak after Zoltan. Cindy, take it away.
Thanks very much, Grace, and thanks, Sarah, for a great presentation, really clearly presented. Grace has already asked the first question I wanted to ask about the R19 expiratory and inspiratory relative values, but I wanted to hear your thoughts about the fact that it seems like a lot of your data, including that the results from R5 minus 19, might actually be driven by the changes in R19 instead of the small airways. And then the other thing I wanted to ask was, is like Peter Cavalier, I was also quite intrigued by the reactants, and you saw some really profound changes in reactants down to about minus 20 centimeters of water seconds per liter from memory. And you've already talked about going back to the data to look at the actual tracings to eliminate potential problems in the resistance, but it might occur in the reactants as well. Like I think especially that transition between inspiration and expiration often, at least I remember a lot of patients tend to have trouble keeping their glottis open at the end of expiration. And so I wonder if you might already have weeded out those people or those tracings.
Yeah, so just hitting on your last point with the contribution of glottis breaking, this is something Ron has brought up, and we have reviewed the data for artifacts and tried to cut that out. But I would love to have a more experienced eye to go over that and make sure that we did a very thorough and good enough job, or the best of job we could, to eliminate that effect. And back to these patients with large swings in reactants between the inspiratory and expiratory phases, as I mentioned, we haven't dug into this too much and how they differ clinically, but we have looked at some of those names of patients that really stood out, and they happen to be these complexing cases that Dr. Nair is dealing with. So I think there's something quite interesting there that we may be overlooking, and that oscillometry could help us understand.
Actually, now that you've brought that up, like I think a lot of severe asthma patients, my understanding is they have upper airway coexisting conditions, which might also affect your R19 more strongly than your R5 minus.
It's very common.
Yeah. So thanks, Charlie. And thanks.
Okay, Jeff, you've got some pearls of wisdom for us.
Thank you, Grace. Wonderful talk. Yeah, I was also intrigued as Peter and Cindy in the reactants. So the reactants was very, very sensitive, the whole breath reactants to your differences. And so when I think of reactants, I especially in asthma, I think of recruitment and de-recruitment, especially with bronchodilator, before and after bronchodilator, which I think is a good explanation. It doesn't capture everything, because there's chest wall stiffness and there's other things in the reactants, but likely those don't change with bronchodilator. But what didn't happen was it didn't change much during inspiratory and expiratory, but R5 minus 19 did. Mm-hmm. So R5 minus 19 is an interesting measure because it's subtracting two things, and if they change together, it won't change. So one of them changed differently than the other. But we usually think R5 minus 19, well, that's heterogeneity, and we think reactants de-recruitment, at least that's what I think, and we think they're very similar because they're likely occurring at the same place. But what if they're not? R5 is generally, especially in asthma, more peripheral because that's where heterogeneity happens. R5 minus 19 measuring actually that difference. And R19 is more central because it's more of the homogeneous component of resistance. But R19 doesn't necessarily reflect the same locations that X5 does. X5 is kind of looking at one part of the lung, but R5 and R19 are looking at two different parts and subtracting the other. And so I think that helps understand that they don't necessarily have to fall to be the same thing. And I think Cindy's idea that maybe the issue is that R19 is doing something quite different than reactants and R5 might be doing similarly, if that simplifies things. But I do love the idea that turbulence might play a role, especially since you looked at the point at which these changes were at looking at the traces. And I think that may be the difference. Turbulence is not likely to be in the periphery, right?
Yeah, it's interesting. So the reason why and thanks for those comments, Jeff. The reason why I really, started looking at this was my passion, my focus is pulmonary imaging and assessing ventilation with MRI. And that's an inspiratory maneuver. We breathe the gas in, and then we take an image of the snapshot. So I wanted to look at these differences to really better understand, is that inspiration reflective of resistance at tidal breathing, or more so inspiratory? And that's kind of what led us down to this rabbit hole of non-experts in oscillometry looking at this. So I very much appreciate everyone's insight.
If we could move on to Zoltan next, and then we'll end with Dr. Irvin. Oh, Leonard's got his hand up too. We might get there. Zoltan.
Congratulations, Sarah, for this very nice, thought-provoking talk. Actually, my concerns were very similar to comments from Peter to Jeff. So reactance is the most provoking inhomogeneous behavior in this population, and probably reflects the most the heterogeneous composition of this group. So whereas, for instance, the resistance measures move quite homogeneously throughout the protocol, pre and post bronchodilator, between inspiration and expiration, etc. My concern is what these mean values during inspiration and expiration reflect. So I think that it's unfortunate that these average values embed both the flow-dependent and volume-dependent components, plus the change in the homogeneity of the periphery during the tidal breath. So a useful addition to this within breath, or I would probably say inspiratory and expiratory and total approach, would be the interbreath, which picks up the zero flow and expiratory and inspiratory conditions where flow is not involved. And the difference between the two is probably more clearly related to the volume dependence and the improvement or impairment of peripheral inhomogeneity. And these two aspects probably on top of each other would represent a more comprehensive idea or description. But anyway, it was very nice, and I agree that it's an ideal talk to conclude a 4-day session.
Thank you very much, Zoltan. Dr. Irvin.
Well, drawing on 18 years of measuring lung function in the worst patients in the United States with asthma, the National Jewish, I'll tell you what you're looking at. The lung is trashed. That's a technical term, by the way. Everything's bad. We know that in this group, vocal cord dysfunction, very common. We know the central airways have been remodeled. You probably see that really nicely with a CT scan. We know from wedging the bronchoscope, where you can make a direct measurement in severe asthmatics, that their lung is closed down. And the MRI data that Grace and other groups have done clearly shows that. Some of that reverses, it's temporally reversed, and some of it's pretty fixed. Well, one of the things you'll learn when you stick a bronchoscope into a severe asthmatic is the airway is full of all kinds of things. It's full of bubbles, it's full of sputum, it's full of mucus. The mucus is cross-linking, so you get mucus plugs. So you've got a lot of trash in the airway, and that's going to result in a lot of variability, which is what you're reporting. you're going to see differences from inspiration to expiration as these bubbles form and close. And I think that's what you're getting at. And I think deconvoluting the stuff we measure with an oscillation into a structural construct is going to be tricky. It's going to require a lot of interrelated measurements and a lot of hand waving. But I agree. This is an interesting group of people to look at, and certainly the clinicians will tell you a real trial to deal with.
I lost connection.
Sorry, Sarah, we're having a hard time hearing you. While we're waiting for Sarah to reconnect or for her connection to strengthen, I'm just going to mention how surprised we've all been about how reproducible the imaging is, how invariable the imaging is, the inspiration.
I'll turn off my video again. Hopefully that helps.
Yep, go for it, Sarah.
Sorry about that, everyone. I apologize. I got cut off when Zoltan was asking, making his comments. So I apologize. I didn't get to hear all that. But I did want to say that I've recently been reading your work on the intra-breath assessments to eliminate the effect of flow on this data.
I think we'll move on to our last questioner, unless Charles, you want to finish that off. But our last question is coming from Leonard Lindblad from Thoracis. Sorry, Sarah, we're just having a little bit of difficulty connecting with you. Go ahead, Leonard.
Thank you. Yeah, I don't know if Sarah can follow this, but I had two thoughts. One was the question earlier about the R19, R20, whatever you measured, and the sort of surprising increase there. And I thought about that when Charlie asked this question too, that maybe that could actually be a central airways component, such as a vocal cord closure or glottal closure or something like that going on in this group of patients. Obviously, that would shift the whole resistance curve upwards in a parallel fashion. So that would be a hypothesis on my part. The other thing I was going to ask you, because I'm not really that well versed in MRI, I've done a bunch of CT before in my life, and we did it, as far as I understand, very similarly to what you do with MRI in mice, that we just inflated them to a specific peep, and then we imaged them at that volume. And as far as I understand, that's essentially what you're doing with MRI as well, that people inhale to whatever volume of pressure, whatever it is, and then you're imaging them. Whereas with oscillometry, we are sort of measuring right around FRC in and out. So I guess I'm just trying to understand how we can use imaging around FRC in order to correlate that with findings of impedance.
Yeah, that's all. Comment on your question regarding the imaging first, and then go back to your vocal cord dysfunction and upper airway collapse. So we acquire these images at FRC plus 1 liter, an inhalation of 1 liter from FRC the patient that holds their breath, and we acquire the image in about 10 seconds. And your point regarding imaging at FRC, we could do that. And there has been, it has been shown that there are patients are less pronounced than if we image them at lower lung volume.
Yeah,
and
thank
then
you.
Commenting on your question about vocal cord dysfunction and upper airway collapse, all of these severe asthmatics have had a detailed workup with respect to vocal cord dysfunction and entrance.
Well,
Okay,
sorry,
sir,
the quality of this was really bad, so we didn't really much get anything of what you said.
Yeah, I'll take over here from here. Let me. So Sarah, thank you very much. It's with a heavy heart that I'm going to invoke closure, because you sound intermittently like you're at the bottom of the sea. I'd encourage you and Leonard to communicate by email or chat. And my final comment to both you and Leonard, it's perfect that we end with a discussion between the two of you, is that you maybe get the 10 hertz modality installed on your TremoFlow, because I think to explore your patient population with Zoltan's intra-breath technique would be very, very instructive for us all, and may help us understand better what's going on. So again, thank you very much to not only Sarah and Grace for a great end of seminar talk, giving us couldn't ask for a better anchor position talk. So thank you very much. To all of you who stayed on past time, we're 52 participants out of it looked like 74 or so at our peak. So Sarah, I think that speaks to the interest that your work is generating. And I didn't mean to imply that you were non-independent. I guess I'm an old man thinking of when you trained with Grace, but yes, you're amazing. And Param is very lucky to have you at the Firestone, and you are doing great work. And we're looking forward to the stuff that's going to come out of your lab in the future. So again, everybody, thank you very much for your participation through all 4 sessions. As I said at the beginning, I hope to welcome you in person to Montreal the last Thursday and Friday of July. And we can catch up in person. And in the meantime, please all stay well, network amongst yourselves. And I'll be very happy if some collaborations and papers come out of this seminar series, because you've heard of ideas and we're able to bounce them off people you otherwise wouldn't network with. So I'm going to shut up now and let everybody sign out. Thanks again.
Bye. Charlie, too much.
Yep.
Gotta have fun, guys. We have to have fun.
Absolutely. Always, my friend.
Hey, thanks, Ron, for doing this.
Thank you, Ron. Thank you very much, Ron.
Yes.
Big gold star.
That was great. That was great, Ron.
Yep.
Take care.
Bye-bye.
Ciao.
Bye.